Okay, here's yet another now you try exercise. So let's take a look. For this one, we are working with pointed sets. So that's a set together with an element of that set, and the notion of strict maps between these pointed sets. That means that it's a map between the sets that strictly preserves the point. So if we apply the function to the point of A, then we get the point of B. And we have this handy way of proving that two such strict maps are equal. It's enough if the underlying functions are equal. Then we have a category of pointed sets and the dimorphisms of strict maps. And we want to get a point for free, so to speak. So we first of all, we want to have a way of forgetting the point and then adding a point in, and then we want to show that these things are junctions. So let's start by forgetting the point, because it's easy to forget the point. So what do we need to do? Well, we get given an object x, which is a pointed set. And we can see what x is. It's given by a carrier. Let's call that x again. And the point, little x. Right? So carrier is the set, and little x is an element of that set. And now here we're supposed to return just the set. So we forget about the little x and just return x. And similarly, is this factorial? So we get given a strict map f, and we get given something in the carrier of A, that's little a, and we have to make something in the carrier of B. So let's see what f is. Well, it's some function f and a proof that this function really preserves the point. Let's just call it p. What we can do here, of course, is we can just apply f to A, and that's going to do what we want. So in fact, we need to take this argument, we can just return the f directly. Okay, does this preserve identities? Well, the way identities were defined in pointed sets here, you see that the identity underlying function is just the identity function. So indeed, that's going to be preserved. And the underlying function of composition is the composition in set. So that's also just going to be preserved. Okay, so that's how we forget the point. We take a pointed set and we throw away the point and prove that the function preserves it. What about adding a point? So this is a little bit harder, right? So here we get just the set x, and then now we have to make a pointed set. So we could try to say, okay, a pointed set is something comma something, right? So we have to give a set, and then we have to give a point of that set. So we could try to just use the set x here, but then here we have to give an element of x, and we don't know if x has any elements or not, right? So that's not going to work. So instead we should try to make an element of x somehow in the least intrusive way. And as these inputs suggest up here, then it makes a lot of sense to use maybe x as the new thing here, right? Because maybe x always has nothing as a point. So we're keeping all of x, but we're adding in one more point, which is nothing. And then here we can see if we're given a function f from x to y, then we have to make a strict map. So a strict map, let's see, did you open the strict maps? Yes. I think it should be something comma something, yes. Okay, and then here now we need a function from maybe a to maybe b, but we have maybe dot map of f, which does that. And then here we need to show that this function preserves the point, but that just means that nothing equals nothing, right? Because maybe map is going to turn nothing to nothing. So that wasn't so hard. Okay, does this preserve identities? Well, what we need is that maybe of the identity function. Is this right? Sorry, this is a bit confusing. So maybe map of the identity function, which is defined to be this maybe combinator, which turns just to just and nothing to nothing. That should be the same as the identity of pointed set. And we have a way of showing that these things are equal, right? Here we just need that the underlying functions are equal. And it looks like here, something like this. What does it say? For every x1 of type maybe x, if I apply this left-hand side to that, then I get the same. So use extensionality together with this to give me exactly what I want. Do that a bit slower if you want. So here now we need to say for every x of type maybe a, the maybe identity applied to x is equal to x, but that's exactly what this thing from the library proves. And similarly here, again we're going to start, we need to show that we preserve compositions. So we start by using combinator we have for doing this. And then here again we have an equality between functions, so we use extensionality. And then we see that this maybe map compose proving exactly that. Okay, so we define the functor the other way, and now what remains to be done is to show that we actually have an adjunction, so we are freely adding a point because we are left adjoint to the forgetful functor. So let's see, what do we need? Now, here we are giving a strict map, so that's f and it proves that it preserves the function, and we have to make an ordinary map here. So we get given an x, and we have to make something in a carrier of b. Let's see, f is going to give something to us in the carrier of b, if only we give it something in maybe x, and we have a little x, so we can just apply just to make it so, right? And going the other way, we start with just an ordinary function, and we have to make a strict map. So the underlying function is supposed to go from maybe x to carrier b. Okay, so let's see. Well, we get given an x. Okay, so now this x here is a maybe type, right? So we could pattern match on it. That seems to be a good thing to do, because if we actually get just x out, then we can feed that to the f, and that should be good, right? So in this case, we do f of x. That's what we want. What about in this case? So here, we didn't get an x out, so we can't use the function f, but thankfully, b is a pointed set, right? So if we just bring that into scope, so now that it's a point little b, so here could return exactly that point. And if you think about what we need to do, we need to preserve our point, which is nothing, and send it to the point of b. So this is really the only thing we should do here. Right? And then here now, let's see, then we just need to show that this function applied to nothing is equal to b, which it is. Okay, so we managed to define functions in both directions. Can we now actually prove that they are inverse of each other? Let's see. Here we are given an h, and we have to show that this complicated thing is equal to that thing. But we have a way of showing that these strict maps are equal. So let's have to look at the underlying things. Is this function equal to that function? Well, let's use function extensionality to see. Okay, so here now we get given x again. We have to show that the functions applied to this x are equal. So because the left-hand side is pattern matching on the x, we should do the same thing. Right, so let's do that. In this case, we see that both of them are just applying the function h. They are equal. And in this case, well, REFL doesn't work here, right? Because we need that the point of b is equal to fun h of nothing. But okay, pattern match on this h, so it's an h, and I prove that it preserves the point, and that is precisely the point. because this proves that a to nothing equals point to b. So if we just sim that, we have exactly the equation we need. Okay, what about in this situation? So here we go, given a k, and we have to show that lambda x k of x is equal to k, but that is always true by reference. That was easy. Okay, here for naturality we get an f and a g, and we have to show that this thing is equal to itself, this. So we managed to prove that there is an adjunction between adding a point and forgetting it again. And what is the monad reduced by this adjunction? Well, the monad you get by composing this functor and that functor, right? So first we add a point, so that's going to turn x into maybe x with a special point nothing, and then we forget about the point again, so that's going to turn this thing into just maybe x, right? So it's in fact the maybe monad that we get by composing these two functors. So that's how the maybe monad arises, as going via pointed sets and adding a point and then forgetting it again.